Good afternoon, everyone, and thank you all for coming to today's seminar. So it is my pleasure to introduce our speaker today, Professor Julia Greer, and actually welcome her back to MIT campus. She did her undergrad here in the chemical engineering department, and after that went to Stanford for her PhD, and after a few years at Intel and Park, joined Caltech faculty in 2007. And since then, she's been at Caltech. So Professor Greer's research focuses on design, fabrication, and characterization of classes of materials with multi-scale microstructural hierarchy that combines three-dimensional architectures with nanoscale properties to lead to many unique applications, both scientifically and also with many technological applications. So her outstanding career and research contributions have been recognized by many prestigious awards and honors. I'm just going to name a few of them here. She's been the recipient of the 2019 Heger Award. She's also been named a Vannevar Bush Faculty Fellow by the Department of Defense and one of CNN's 2020 Visionaries. Professor Greer is the director of the Kavli Nanoscience Institute at Caltech and also serves as associate editor for Nano Letters and Extreme Mechanics Letters. What is very interesting to know is that beside her outstanding career in research, Julia is also a concert pianist and very, very well accomplished in that area as well. So it is our pleasure to have Julia here with us today, and we're excited to learn more about her research in three-dimensional architected metamaterials. Thank you, Julia.
Well, a huge thanks to all of you for coming. A huge thanks to Farnaz for inviting me here. And a huge thanks to all of you for being here. It's always such a special feeling to return back to my alma mater. It's like I'm going through all the same corridors. And it's like this used to be my life, and now I'm a colleague. It's crazy. So I usually like to keep my seminars interactive, so please don't wait to ask your questions. Please ask them as we go. All right? All right, let's begin. So you've been staring at this title for some time now, Materials by Design, so perhaps that part makes some sense to you. And then you look at the second part, and it says, chemically derived three-dimensional nano-architectures. Kind of made me wondering, like, I think I know what each one of these words means individually, but why they belong in the same sentence might be a little less obvious. So the goal for my talk today is, in fact, to convey to you why they do belong in the same sentence. So imagine a situation like this. I suspect many of you are familiar with this. You go to the store and you get all these things that you absolutely need to get, and the bags are just not quite strong enough for that. And this is not the only example. From the wine glass that never makes it to the toast, to the helium-filled balloons that pop all too easily, to the I really meant to have 4 children situation. So these are all examples of materials that are lightweight, and because they're lightweight, they're very easy to damage and to tear. Turn on the mic. Okay. Is there a button?
Yeah, it's on the top of the...
How about now? Is this working?
Yeah. Yes.
Can you guys hear me? Everybody can? I've never been accused of being too quiet. All right. Okay, so these materials are all lightweight, and because they're light, they're easy to damage and to tear. So let's look at the opposite end of the spectrum. Let's look at the materials we know to be strong and we know to trust. So here's, I am particularly intimately familiar with one of these, but many of you travel, of course, right? So Boeing 747 weighs nearly 1 million pounds. So when you do a back-of-the-envelope calculation at 5 gallons a mile for about $2 per gallon, my trip here should have cost about $30,000. So thank you very much for reimbursing me. So this tremendous expenditure in the airline industry comes, of course, from the fuel that's required to propel such a heavy machine through the air. And of course, the Dreamliner has already reduced the weight by about 50%, and that's what enables it to do some serious fuel cost savings. Now, another example of materials that are specialized, they serve a particular function, a solar cell. We know in California, we have a lot more of the fuel for the solar cells. So imagine if either one of these falls off the roof, accidentally slips off. This is going to be bad news, of course, for everyone. So these are single crystalline silicons, a very brittle material, right? So this would be a bad situation. So speaking of materials that are too heavy, remember how in the last decade we were discussing this concept of space elevator? Well, as far as I know, there still isn't one. And the reason for all of these problems is this. This is a busy plot. So what I'm choosing, well, I'll walk you through this. What I'm choosing to plot here is the strength, but it can be any other mechanical attribute. So if you plot the mechanical resilience of some sort as a function of density, what you see is that there's these colorful domains of all the material classes that we know today. So the picture that emerges right away is that we're very good at making materials that are simultaneously strong and heavy or simultaneously lightweight and weak. What we're not so good at is making materials that are very, very lightweight, but also mechanically resilient. So how do we do that if everything we already know how to make today is already plotted here? How do we get into the so-called white space? Now, this is a log-log plot, so even a small increment within this space already represents a substantial change. So the way we do this is by utilizing the concept of architecture in material design. So when you look at the largest, this is the largest stone man-made monument, right? So the Great Pyramid of Giza, you can see it's very heavy. It's very, it stands about 150 meters tall, and it weighs about 6 million tons. That's very, very heavy, right? So in contrast to the Eiffel Tower, which stands twice as tall and uses 1,000 times less material to construct it and is just as mechanically resilient and presumably used a lot fewer slaves to construct it. So that's the idea. So when we first began this research, it was these nickel microlattices, and this was a collaboration with HRL. Now, there's nothing special about this dandelion. This is the world's most normal dandelion, not the strongest dandelion, nothing. And you can see that this nickel microlattice is hardly perturbing it at all. And in fact, if I were to hold a microlattice in one hand and a feather in the other, and to release them at the same time, the feather would fall down faster. They're very, very lightweight. But what we're after is not just the lightweight, but it's the combination of the lightweight and the mechanical strength. And for that, you have to go down 3 more orders of magnitude and dimensions to the nanoscale. And I believe this is what the unifying theme here is of all of you here, is that you care about different nanoscale phenomena. So what I'm showing you here, is it possible to dim the lights by the board, by the way? Is there just a separate, yeah, I'm going to show a lot of SEM images and CEM images, and so I think it might be better to dim these lights. But anyways, you can, oh, perfect. Thank you. Is that too dark?
No, it's good. It's perfect.
Is that okay? Just don't fall asleep. I'll try to keep you all the way. But I think this is a much better quality images. So the first thing to show you is that we're not limited to periodicity. So this is, those of you who are fans of Doctor Who, this is a micro TARDIS. So it's about 1/10,000th of your hair diameter. It's very small. You can see the rest of these architectures that were made in our group are examples of cellular solids. And so there's an obvious level of porosity that is immediate to see, and that is that they're cellular solids. And so mostly they're comprised of air. They're very open architectures. The less obvious level of porosity here is that the beams, the tubes that comprise, these are the nanoscale building blocks that comprise these 3-dimensional architectures, are hollow. And the wall thickness here can be on the order of 5 nanometers, maybe 10 nanometers or something like that. So when you look at these materials, they embody every length scale from some nanometers to hundreds of nanometers to microns, and then eventually hundreds of microns, and eventually we'll scale them up to meters someday, sure. So the largest dimension of these solids is just the wall thickness. So when it sits on your hand, it looks like a solid cloud that's sitting on your hand. And you can see the versatility of these architectures. So because of these different length scales that a single material embodies, it's no longer possible to describe them from just a structural perspective or a materials perspective, because at those length scales, everything is coupled together. And here's what I mean by that. Nearly all common metals exhibit size-dependent properties. So this is a so-called size effect. When you look at the metals we're all familiar with, so copper, nickel, gold, something like that, and in their single crystalline form, so no grain boundaries. So defects, no problem, but no grain boundaries. What we and many others have now demonstrated is that as you reduce their dimensions, their strength increases tremendously in a power law fashion. And what I mean by that is that if you take a chunk of gold, which we know to be very malleable, and you reduce its dimensions to about 200 nanometers, it becomes as strong as steel. So smaller, in this case, is stronger. Now take exactly the same metals and deposit them using a different technique, using CVD, using sputtering, using all these wonderful tools that you will eventually populate your beautiful facility with. And all of a sudden, this effect is reversed. All of a sudden, smaller becomes weaker. It's a more modest size effect. It's no longer in a log-log plot. Nevertheless, it's real. So what you start to realize is that it's the combination of the atomic level microstructure and the reduced dimensions of materials, metals in this case, that give rise to the tunability and strength. Now, the size effect is actually more powerful than that. We all know glasses to be brittle materials, right? If you look at this special kind of glass, so this is a metallic glass. Now, the dimension here is about 150 nanometers. And you pull on it, what is supposed to happen is that it'll shatter, right? So we all know the glass can't possibly be extended. So watch what happens here, and especially look at this region right here. So this is 150 nanometer diameter glass, and you can see it's forming a neck. So it thinks it's a metal. And in fact, you can extend it by about 100% before failure. The last example I want to show you is the deformation of a single unit cell of a ceramic nanolattice, so just a single unit cell. Now, this is titanium nitride. It's a very, very brittle ceramic. And you can see what's happening here. Each one of these beams is bending. And if you were to calculate the Mises stress and then to extract the tensile component, it exceeds 1.7 GPa. No ceramic should be staying intact when you apply 1.7 GPa of tensile strain, tensile stress to it. In this particular material, not only is it staying intact, but it's doing that over many, many, many cycles without failure. So the takeaway message here is this. Sometimes materials get stronger. Sometimes they become weaker. And sometimes you can suppress brittle failure. But all of these effects emerge only at the nanoscale. So the question was, can we somehow harness all of these beneficial size effects, the nanoscale phenomena, and proliferate them onto the three-dimensional architecture so that we can make large dimensioned materials that retain the nano-sized properties? And so just a few words about how we make these. So we use a technique called two-photon lithography. And the instrument that does this is called nanoscribe. Do you have a nanoscribe here? So how many of you have used a nanoscribe? Well, I highly recommend it, in case you don't. The advantage here is this. So in contrast to the UV lithography, which I think as many of us are familiar with, the light in a two-photon lithography, the light is focused in a voxel. And this voxel is submicron, and it can be rastered in space, so in three-dimensional space. So in each individual femtosecond laser pulse, now the constructive interference of exactly 2 photons gives rise to this type of resolution. And then you can raster that voxel in 3 dimensions to write whatever shape you want. So there's no mask, there's no periodicity. This is why we're not limited to periodicity. And complexity comes for free. So I can write a nano Vladimir in the same amount of time as I can write a nano cube. So a very simple versus very complex here comes at the same amount of time, which is not very fast, but that's a separate challenge. So when we write this scaffold, we often write it in this kind of form. So it could be periodic 3-dimensional architecture. But then this is made of a photoinitiatable polymer resin. So we're not going to go and build airplanes out of polymers, right? So we then coat it with a material we actually want in some parts of our research. So do you have an atomic layer deposition system here? How many of you are familiar with ALD? OK, so in the ALD community, you know how they say, oh, we can deposit anything you want as long as it's alumina. So here's some alumina ALD depositing conformally around these complex architectures. And then what was so painstakingly written, this entire scaffold can be etched out. And what you're left with is a replica, a hollow replica of what we had designed. So here's the real time process. And so first we align it in the microscope, of course, and then we start writing. And so you can see that you can label very easily. You can write things very easily. So this is defining, in fact, an architecture in real time. So it's not slow, but it's also not exactly manufacturably fast. So we have to torture all of our samples that we produce in a special instrument because you can't exactly see them. And this right here is just an SEM chamber. And with all the whistles and bells that we attach to it, it enables us to perform different kinds of experiments. So this, for example, is a nanomechanical module that's similar to a nano-indenter, so we can perturb things mechanically. This is a cryogenic module, so we're able to conduct these experiments at different temperatures. And this is an electrochemical module, so we do quite a bit of work in electrochemistry in situ. And these are all the different inquisition devices, so we push on them and pull on them and torture them in various ways, just to show you the difference in length scales. So for example, the opening here is about 200 nanometers, so it's very small. Now, back to our hypothesis. Can we harness the size effect and proliferate them onto the larger scales, right? So this is an octet nano architecture. So it's supposed to be particularly stiff. The wall thickness here is 50 nanometers, so they're all straws. Imagine like your straws. And so they're comprised in these 3-dimensional cellular solids. And we're going to to compress it. So it's 99.9% air, very, very brittle ceramic, right? ALD alumina, very brittle, and we're going to compress it. So what do you think is going to happen? It's not a rhetorical question. It's going to shatter. Of course it's going to shatter, right? It's your coffee mug with a severe case of osteoporosis. So we're loading it, loading it, loading it, and bam, it shatters. It doesn't even try to recover. This guy is dead. We have a little nano-seminar in our instrument. But the walls are only 15 nanometers thick, so that's pretty small. That's pretty nano, right? So shatters, it crushes, and dies. Wow, your VGA connector here is wonderful. Thank you. Sorry about the videos. So it crushes and dies, right? So now, in contrast, oh my gosh. In contrast to this never happened before. In contrast to this kind of situation. So now let's repeat exactly the same experiment, and the wall thickness now is only 10 nanometers. So we're reducing the wall thickness by a factor of 5. And let's see what happens. So it should crush and die even more readily, right? And so we're compressing this very, very brittle alumina and almost to 50%, and we're expecting it to crush and die even more readily, and it fully recovers. So if that doesn't convince you that there is, in fact, a size effect, I should just go back to the MRS right now. So the only difference between these two is the wall thickness. It's exactly the same microstructure, exactly the same everything else. So that fully recovers. So now, since that time, we've actually uncovered quite a bit of complexity. We've built in quite a bit of complexity, both to the loading stress state as well as to the actual architecture. So here's a comparison between periodic and aperiodic. So this is this bicontinuous labyrinthine architecture. You can see that it recovers and absorbs energy in a very efficient way, just like a periodic architecture. So it's very much random, conducive to randomness, as well as to periodicity. And notice how this part of the sample doesn't even know that it's being compressed. Now, you can build different densities, and you can build in gradients, you can build in trajectories in such a way that, for example, here, the lower density part, of course, deforms first, but not only that, it deforms fully before this part even realizes that it's being compressed. And so you can see that this is being manifested in the stress-strain data as well, so you can build in the trajectories of deformation that gives you the tunability in that. Now, you can make your architectures be very complex. For example, this is a fractal type of a nanolattice where each individual beam is now comprised of self-similar unit cells. And you can see that this kinking is starting to happen in the lowest order of hierarchy. And I'm watching, and this is going to snap. Every time I watch this video, it kind of hurts. And you expect it to snap right there, and it fully recovers. So you can see that this recoverability, just one second, prevails under complex stress states in complex architectures over many, many cycles. Yes?
What's the deal with the first cycle in the bicontinuous labyrinth? The first cycle seems
The first cycle is not in bicontinuous. That one is in the other one. The orange one, I think, is the cellular one. It's always the first cycle. First of all, is always different because that's where you build in. I think it's the architecture. It's the layer by layer collapse. So each individual undulation corresponds to the layer by layer collapse, and you introduce just a tiny bit of damage. And so after that, it's just elastically sitting and cycling many times. But the first cycle is always different because you introduce the initial pre-damage into it. All right. So skipping through all that. OK, so would you like to know why this happened? I mean, this recovery is very surprising, and ceramics are not supposed to do that. So let's tackle this from the mechanics point of view. So this is a hollow beam-based architecture. So the only way that beams, especially hollow beams, can undergo an elastic instability and recover eventually is through shell buckling. So this is a special type of buckling, which is effectively through these, well, then it's called shell buckling. And the idea here is this, that if you have a beam whose wall thickness is T and the radius is A, if you can set the failure criterion such that yielding would occur, of course, at fracture because it's a brittle material, versus local buckling, and you can determine what this ratio is, the critical ratio of T, the wall thickness, over A, such that below this critical ratio, your material will buckle, and above it, it'll fracture. So let's see if this is what happens here. So at the 10 nanometer wall thickness, that critical ratio is 0.016, which is below 0.03, below what we calculate for this material. And you can see that, sure enough, it recovers for every single type of unit cell. This is the image for after deformation. You wouldn't be able to tell because it looks identical. And as we increase the wall thickness and get close to and then exceed the critical ratio, you can see that the deformation becomes much more stochastic, much more jerky, and there's certainly no more recovery. Well, if that is the case and mechanics has all the answers, that means that if we were to build a building whose wall thickness is 10 centimeters and whose radius is 3 meters, as long as T over A is below 0.03, if we were to build a building like this, it would totally snap back. If some giant came and stepped on it, it would spring right back, right? I'm so glad that you're laughing because, good, because that would never happen, right? I'm sure there's a building like that in Singapore somewhere. Why not? So if the mechanics has all the answers, T over A is scale invariant. So something else, the size effect here is manifested through something else. It's implicit. So how does it manifest itself here? Why is it that the 10 nanometer thick structure would recover, but a 10 centimeter thick building that has everything else the same would not? Also not a rhetorical question. Yes? This is it's just alumina. Yeah, no, it's an amorphous material. There are no grain boundaries, but there are also no dislocations or anything. Like, it's just amorphous, brittle. Good guess, though. Any other ideas? It's a brittle material. Are there any mechanical engineers type people here? Material. You are a professor. You're not supposed to know. Yeah, that's exactly right. So brittle materials fail at flaws. The probability of finding a flaw, 1,000, a million flaws in something that's 10 centimeters thick is 100%. You're going to find a distribution of many, many flaws. There's some weak ones, some strong ones. But the point is that under a globally applied stress, the local stress field ahead of one of these or many of these defects will exceed the fracture strength. So before these tubes ever get a chance to experience buckling, your material will locally fail. In contrast to something that's only 10 nanometers thick, first of all, the size of the largest flaw is only 10 nanometers. And secondly, the probability of finding a flaw is much, much lower. So the size effect manifests itself here by our ability to make much more perfect materials. If we were to make something that's only 10 nanometers thick and then to fill up this whole room in the same volume versus a monolithic material, we will make a much higher quality material. And so that's what gives rise to this, to these unique phenomena. So the right answer was no, in case you were wondering. OK. So the original question was, did we hit the white space? Remember that? And how close can we get to the theoretical predictions? So this is the original plot. And this is some of our data. So this data is from a while ago. It's from 6 years ago. And we can do much better now. And hopefully, maybe some of you can do much better now. Here's an interesting data set. These are the fractal nanolattices. And you can see we bought ourselves 2 more orders of magnitude in reduction in density. And so we certainly have ventured into the white space that hasn't been uncovered before at that time. And then even here, like I said, even a modest increment within this log-log space already represents a substantial departure from current. What we also shown much more recently is that some materials are, in fact, much closer to the theoretical strength. So for example, carbon, and I'll tell you a little story about carbon. These are all the new data points that just came out, I think, this year. You can see that in the higher density regime, they can actually get to the theoretical limit. And one should always question, what exactly is theoretical limit? How do you define that? Well, of course, you can't be stronger than the atomic bond. But once you start talking about something that's a nano ribbon that's wrapped around a 3-dimensional architecture, it's not quite a 2D material because it's not just a single atom thick, but its thickness is very limited, and so your surface to volume ratio is very high. So theoretical strength possibly needs to be redefined for these materials, and I'll just leave you with that. OK, so this, of course, all of everything I've shown you up to this point brings up quite a few mechanics questions, right? So what is the effect of architecture? What is the fracture behavior? So I only showed you compression experiments. We've done quite a lot on tensile deformation and on fracture behavior. Defects, very, very important. How to optimize this? And then I call the second and third harmonics of these questions because, of course, each one of these questions brings in its own hierarchy. But that's not what I'm going to do right now. What I'm going to do right now is take a little poll in the audience here because I'm going to tell you only one of these 2 stories. And I managed to classify them into 2. One story could be, it's called More Mechanics. So I can tell you a bit about the mechanics of batteries and energy storage systems. I can tell you quite a bit about the dynamic impact. In fact, we have a collaboration with Keith Nelson's group here doing lipid experiments, so laser impact type experiments. I can tell you a bit about fracture and about flaws. Or another story I can tell you is the story of additive manufacturing. So this is the story that gives rise to the chemically derived part of the sentence that I aim to explain. And that is, how can we create these kinds of nano-architected materials out of not polymers and out of not ALD ceramic, ALD alumina? How can we make them out of metals? How can we make them out of metal oxides? How can we make them such that they exhibit unique nanophotonic properties or some other, or energy storage kind of properties? So that's what this story would be about. So this is more, and I will tell you, I will finish with a story that combines all of it together. So nobody will feel cheated. Okay, so could you stare at this for maybe like 2 more seconds and then prepare to vote? So everybody can vote once and has to vote once and only once. All right, so who wants to hear more mechanics? Wow, all 3 of you. Okay, great. And who wants to hear about additive manufacturing? All right, I guess that's what we're going to do. So this is the only time I actually need to touch my computer. Those of you, I will be happy to share the mechanics story as well later. Okay. Okay, so one feature of Nanoscribe is that they're a little bit, you can buy the instrument, but what they really get you with is the resist that you have to buy from them. So there are these 2 commercial resists, the IP-dip and IPS, and those are the ones that they pretty much control. But if you have very clever Caltech graduate students, you realize pretty quickly that you don't have to be a slave to these resists. And so what my student Andre demonstrated is that actually you can take a MOF, which is a metal organic framework. And so what you can see here is the nickel ion that's embedded into an organic shell. And it can undergo a ligand exchange reaction where you can take this nickel ion and now surround it with acrylate groups. And it's the acrylic-based polymers that enable the photoinitiatable reaction. So the question was, can we then take this nickel acrylate and combine it with a photoinitiator? We tried this maybe a couple of years ago. This is relatively new approach. And just to see if we can even print something with it. So that's what Andre did. So turns out that you can incorporate this nickel resin into the acrylate as long as it's able to cross-link and undergo the photoinitiatable reaction. And watch what happens. So the unit cell here is on the order of 10 microns, and the beam diameter here is on the order of 2 microns. So that's the resin. That's the nickel-containing resin. So what do we need to do to get rid of all this organic junk? Because really, ultimately, what we want is metal, right? We want the nickel. What do we do with the organics? We burn it off. And the fancy word for burning is pyrolysis, of course, right? In a nitrogen-free environment. So it turns out what we learned is that when you pyrolyze something and you volatilize all this other stuff, it shrinks tremendously. It shrinks by 30% in each linear direction, which means that volumetrically it shrinks by about 90%. And so what we end up with is an additively manufactured nickel nanolattice whose unit cell size is 2 microns and the beam diameter is below 500 nanometers. It's tiny. So we just additively manufactured the smallest additively manufactured nickel material. Well, the question, of course, is, well, all right, how nickel is this nickel? This is all chemically derived and all that. So we did some EDS analysis. So this is energy dispersive spectroscopy that shows that there's quite a bit. It's pretty much all nickel, more than 90% nickel, with some oxygen and carbon. Well, okay. It's not really sufficient to know the chemical composition. We really need to understand what form this nickel is in. So how many of you have ever prepared TEM samples? I saw a beautiful Titan instrument down below. So you must have some TEM. So how many? Okay. So you know it's pretty painful to make the TEM samples, right? How do you take a tiny little structure with 400 nanometer beams and then convince them to go onto the TEM grid so that you can analyze it? Well, you can use the fib, but then you're introducing gallium ions, right? So that's bad news. So Andre was particularly ambitious, and he said, well, what if I write a grid on a grid and then just really hope that one of these beams happens to subtend a hole in the holy carbon TEM grid? And sure enough, he did. So this is the most unadulterated nickel, additively manufactured nickel beam that happens to be here. And so we're able to do quite a bit of TEM analysis. And what you see here is that it's pretty much all nanocrystalline nickel. So here's the diffraction pattern with a mean grain size of about 20 nanometers. And then there's also some nickel oxide and nickel carbide, just a little bit of each. And the oxide probably formed just a surface native oxide. So let's look at this nickel. So it's nanoporous. You saw it was very porous. It's nano-grained. That's bad news for any of you who do metallurgy, or for any of you who are material scientists or mechanical people. That's a really, really poor quality. At bulk scale, that would be a very poor quality material, right? Nobody wants porous because they're all flaws. And nobody wants nanograins because that makes the material be brittle. So let's see how it does mechanically. Okay, so here we are compressing this nano-architected nickel. And okay, so it looks like it's behaving exactly like it should. This is the telltale layer by layer collapse. That's very characteristic of cellular solids. You can see that it densifies in this part. And then you see, look at the stress level here. It's about 10 megapascals. Well, okay, let's see what does it, we don't really know how porous it is, right? So let's compare it to some other additively manufactured metals out there. And here's the picture that we were very surprised to see. If we were to apply the specific strength here, so that means strength normalized by density, right, of all these different metals that were necessarily additively manufactured. And so here's some titanium alloys, there's some silver, I think, there's some aluminum-based materials. And we plot them as a function of beam size, and that is the smallest dimension that they created. What you see right away is how rapidly the strength deteriorates. Additive manufacturing processes are terrific at 1 millimeter length scale and above, right? And then, as soon as you start reducing the dimensions even from 1 millimeter to 100 microns, you can see the strength falls by 2 orders of magnitude. And if we were to continue this trend, our nickel nanolattices should be, we had to put in a break of like 7 orders of magnitude down below. And what you see, the results of our work shows that at the beam dimensions here, which is below 1 micron, right, so 500 nanometers, not only does it hold its own, but it actually compares quite favorably to other additive manufacturing processes on the order of 500 microns. So it turns out that nanoscale allows you to be much more forgiving against defects. So even though at the bulk scale, this material would have been terrible and it would have had terrible mechanical properties, it actually can hold its own pretty well. All right, now, of course, after we did the nickel, Andre decided, hey, this is actually quite enriching, and maybe we can venture into other materials. So the next pursuit using this ligand exchange reaction was the titania. So I guess I'm giving away the answer on the slide here, but there's one interesting property that titania has. Of course, it's photocatalytic. So what that means is that if you expose it to sunshine, it'll generate reactive oxygen species, which can then go and kill microorganisms like E. coli or bacteria or something like that. Now, the big distinction here is this. Look at the scale bar here. This is not a typo. It is actually 5 millimeters. So these weren't created using 2-photon lithography. These were actually 3D printed. And so when you 3D, so they're much larger. So now imagine you put one of these things that you can hold in a dirty water bottle, and then you just put that water bottle and leave it in the sunlight, and it'll kill all of your bacteria. And so that water is actually safe to drink. You don't need to agitate it or do anything else. Right now, this type of titania exists in the form of nanoparticles, and you can't extract them out of the bottle after they kill the bacteria, so you're going to have to drink them. I don't know how many of you want to drink titania nanoparticles. I certainly don't. So the advantage of this is that it allows you to extract the filter after it's done its function. Now here's Andre demonstrating that. So this is the part that contains the microlattice. This is the part that doesn't, and so this is methylene blue, so it's effectively like an E. coli type of bacteria. And you can see, sure enough, it actually deactivates. As you can see here, here's the fluorescence spectra. Now, titania is not only photocatalytic, and actually titania has quite nice photonic properties. So now when you take this type of titania process and reduce its dimensions down to the nanometer length scales, what we can make, so this is titanium made using 2-photon lithography, so it's quite versatile, right? 3D printing or 2-photon lithography, and pyrolyze it. What we were able to achieve is the unit cell size spacing here in a wood pile architecture of about 1.5 microns, which of course is optically near IR, optically relevant. And so what my students were able to demonstrate is that you can actually not only elicit a band gap here. Hold on, I haven't gotten to the band gap yet. Right, this is just to show you that this is rutile titania. So titania comes in 2 different phases, anatase and rutile. And so what we made is in fact rutile titania. And here's what's interesting about it, is that not only can you generate a band gap, but that band gap shifts. So this is the reflectance spectra. It actually shifts as a function of periodicity. So you can now additively manufacture these to tune them properly to be whatever whatever dimensionality you want. And so here's the calculated spectra that shows you the dispersion relation. And then here's the actual data that shows you reflectance versus transmittance in the FTIR instrument. And then it shows how it shifts as a function of periodicity. So there's some interesting nanophotonic effects. Now, many of us in California, and certainly in the world, are concerned with sustainability, right? So when you look at these acrylate-based chemistries, they're not great. You can demonstrate some neat phenomena, but it's not the best waste product. So another student of mine, Daryl, decided that he was interested in designing hydrogel-based synthesis of these materials, so we just use water. And so what he was able to demonstrate is that, sure enough, when you combine the photoinitiators and the chemistries just right, you can start working with metal salts. And so in this particular case, he's working with a zinc ion salt, and you can swell in and out of the hydrogel. So using the same process of 2-photon lithography, you can actually write a zinc-containing nanostructure. Now, in the presence of oxygen, so without the oxygen, the burning is called pyrolysis. In the presence of oxygen, burning is called, does anybody know? Calcination. Yeah, so apparently, I also had to learn that. So when you calcine this, you generate a zinc oxide nanoarchitecture. And so let's see, did we actually, so same thing, did we actually make a zinc oxide? Well, it looks like we did. So here's the zinc signal. Here's the oxygen signal. There's a bit of carbon, of course. This one is even more nanograined. This one is 5 nanometers grained. Remember, the nickel was 20 nanometers. These are very, very fine-grained ceramics. So what's so interesting about zinc oxide? Why should we care? Does anybody, what? Piezoelectric. That's exactly right. We all know zinc oxide to be piezoelectric, and it's single crystalline form, of course, right? This is as far from single crystalline as one can be, so this should not be piezoelectric, right? So let's see. All right, so don't look at the bottom part. Only look at the top part. So here's the resin. This is the zinc-containing resin. So I showed you the cool instrument that we have, right? So it's able to apply mechanical loads and to measure the electrical response. So when we apply, so here's the displacement. So when we apply a step in displacement by about 350 nanometers, nothing happens in the voltage signal when you just have a zinc oxide resin, zinc ion containing resin. Once you've converted it to zinc oxide and you repeat the same experiment, let's see what happens. So now we step it by about 200 nanometers, and sure enough, we're getting a very consistent and reliable voltage drop. So it is piezoelectric. We just fabricated a sensor that is very responsive to displacement, right? So it is piezoelectric. Why is it piezoelectric? It's not single crystalline. What's going on? So all of my questions are really not rhetorical. I would welcome your input. Is anyone else surprised? Right? So the way piezoelectricity works is that once you apply a strain, it polarizes the unit cell, right? And so you create an electric field, so all of your positive charges go in one direction, negative go in the other direction. But it requires, as soon as you have 2 grains and they're oriented differently, it's going to cancel each other out, right? So the electric fields are going to cancel themselves out. Why is this working?
Isn't it telling it's only half a millivolt?
Isn't it what?
Isn't it telling that it's only half a millivolt change?
Yeah, it's a tiny, you're on the right track. That's exactly, it is. It's tiny. It's supposed to be more. So anybody else wants to develop that idea? It's not a lot. So if you were actually to look up the piezoelectric coefficients, all the D matrix, this change is tiny. So it's something like 1 millivolt, right? Something like that. Half a millivolt. Sure, half a millivolt. That's fine. Half a millivolt. So so it should be changing by 2 volts, for example, or something like that. Yeah. That's exactly right. It's simply the stochastic statistical distribution of the c-axis within this multitude of these 5 nanometer grains. So if you were to just do a random distribution and calculate just using very simple analytical calculations, simple rule of mixtures, this amount of voltage drop simply scales with the number of grains that are oriented, whose c-axis are oriented along the compression direction. It actually, when you calculate how many 5 nanometer grains you can shove into a beam that has certain dimensions, it actually all checks out. So that's where the piezoelectricity comes from. So this was, yeah?
Sorry, but shouldn't that show up in the diffraction pattern that you showed before? Shouldn't some
A diffraction? Yeah, it's blocked right now.
Right, so shouldn't some directions be more brighter if there were preferred orientations in the grain?
Yeah, so you can see them light up. So you can see this is the 100 planes, these are the 101 planes, 102, 110. They're all labeled.
No, I'm saying going along one of the rings. If this wasn't a completely random orientation, I would expect to see some brighter spots, right?
They're circumferentially, they're out of plane, they're randomly oriented. The only one that matters is the orientation of the z-axis, so one direction, with respect to the loading direction. And that you wouldn't see in a diffraction pattern because you're just taking a cross-section. Yeah, so it's pretty random. And that's why you don't, I see. Brightness variation within the ring? No, we don't see that. So it's pretty randomly oriented. OK, now we've made some metal oxides. So the question then, of course, is can we then reduce them back to their metals, right? So we made the nickel using the ligand exchange reaction, which is all acrylate-based. Can we now use this hydrogel-based chemistry to create metals? Well, we know how to make the oxides, so can't we just reduce them? And so here's the idea that you basically have this metal-containing polymer, and it's a hydrogel, so you can swell all these metal salts in and out, and you can actually make multi-component systems. And sure enough, you can then reduce in the reduced atmosphere. And so here we go. Does anybody know what this metal is? Copper, very good in that one. Nickel. We needed to demonstrate that we can make nickel using hydrogel-based synthesis. So what you can see is that here's a copper ion swollen hydrogel, which has this pretty blue color. And then you oxidize it. So here's the burnt oxide. And then in the same furnace, you stop flowing the hydrogen gas, or the forming gas, and then you switch to oxygen-containing, or the other way around, the oxygen-containing versus the hydrogen-containing, reducing atmosphere, and it turns into this perfect copper pattern. And the same thing from the turquoise to nickel oxide to pure nickel. So this is a new development in our group that we're able to produce these quite reliably, and they're also multi-component metals, not just a single material. Now, once we've learned how to make all these different kinds of architectures, we are also interested in investigating the chemistry on the surface. So can you functionalize these nano-architectures? What you're seeing here is my student Daryl showing off, basically. He's making all these different chemical functionalities, from Teflon to aromatics to very long alkyl chains and different types of architectures. So he's showing you the versatility both in the architecture and in the chemistry. And the reason why we would want to do that is so that we can attach these. So these would serve as tremendously penetrable membranes. So if you were to, say, work with some kind of membrane, either for water purification or in your body, wicking away excess chemotherapy medication. So what you're seeing here is a pattern of doxorubicin, which is a very effective chemotherapy drug. Unfortunately, it's toxic not only to the cancer cells, but also to the rest of the body. And so this is a demonstration that one of our membranes is able to capture the excess doxorubicin in the bloodstream while allowing the red blood cells to flow through and then to be able to wick away the adverse chemicals. Now, this is some of our latest pursuits, and that is working with Shapememory polymers. So there's quite a bit of work that's done on Shapememory alloys, like nitinol, for example, right, for your stents. But nitinol first of all, can't really be made at very small length scales, so you can't really put it in the eye, like a stent for the eye, for example, or anything like that. And it's a metal, so it's very, very stiff. So what we're interested in is this. Can we elicit this Shapememory effect in a polymer and architect it? And so my student Luisetta is working on this. So she figured out that if you come up with just the right chemistry with cross-linkers and chain builders, and then utilize the glass transition-based mechanism for triggering the Shapememory response, she's using dynamic mechanical experiments to identify the glass transition, because who knows what that is, right? So you have to actually identify it. And sure enough, she's able to demonstrate that flowers, for example, can open their petals and can close their petals. She's using this lattice to compress it and to open it, and so she can measure the recoverability ratios. So she was able to demonstrate that there is actually this Shapememory effect that you can elicit in polymers and then start making useful biological devices. And then, like I said, I was going to talk a little bit about battery electrodes. So one of the directions in our group is to try to make an all-solid-state, three-dimensional architected battery. So one problem, so we can do so the most important thing is the solid-state electrolyte, but there are some electrolytes that can be used with that. But what do we do about the cathode? And so this is a demonstration of using this metal oxide process to create lithium cobalt oxide. So this is a 3D architected lithium cobalt oxide. The first question was, can we even convince the lithium and the cobalt and the lithium and the cobalt to coexist in a hydrogel and to create this material? And sure enough, first we created just the slurry. It's not architected yet. So it's just a slurry to show you that, look, in charge and discharge, they're not great, but they work as a battery. And then can we then add some photoinitiators and the UV blockers here, some more chemistries to try to see if we can write and create 3D architecture. So here's our lithium cobalt oxide. This is as it's going from the ion-containing solution to the actual solid-state electrode. And then when we put it into a real coin cell battery, so here's what you see. So the Coulombic efficiency is actually pretty okay, not great, but pretty okay. And then we can demonstrate the cycling capabilities based on the rate at which we're cycling. Okay, so in the last few minutes, I'd like to tell you a little story about batteries that combines the mechanics, the electrochemical reconfiguration, and most importantly, the defects. So another former student of mine, who's now a doctor, Dr. Xiaoxing Xia, wanted to understand this problem of lithium anode. So silicon anode for lithium-ion batteries. So silicon is a very brittle material, right? So when you lithiate and delithiate it, and there's such a tremendous amount of lithium ions that are going into diffusing into the silicon material. Of course, it's experiencing triaxial stresses, very large triaxial stresses, and trying to expand by about 300% volumetrically, and it can't because it's a very brittle material. Well, it turns out that nanosilicon can, in fact, do that. So what Xiaoxing did is he built a tetragonal nanolattice that's made out entirely of a current collector, which is the nickel here, and the or 100 nanometers thick ribbon of silicon. So this is the top view here, and let's see what happens when you lithiate it. So now he's lithiating it, and he's lithiating it, and you see this pattern forming. So some people may think that it's sinusoidal. I'm a musician, so I think these are violins. Whichever way you want to look at it, here's what forms. So here's the top view in a tilted view. And so from the top view, you very clearly see these sinusoidal patterns. So these beams are buckling in response to lithiation. And that's their way of averting this catastrophic failure. And in fact, because they can accommodate the strain and the lithiation by buckling out of within the plane. And you can see that there are these nodes, and you can see how the beams that subtend them actually buckle between them. But here's, well, and just to prove to you, okay, this is not just a bunch of pretty pictures. It is, in fact, a battery. It's not the world's best battery, but it's a respectable battery. And what I'm showing you here is that here's the lithiation at different voltages. And here's an image after 10th lithiation. Here's a delithiation as we're increasing the voltage. And here's the image after 10th delithiation. Seems like it's doing quite all right. And so here's, we learned that the cutoff voltage should be about 0.6. And under those conditions, in fact, I think here's the 0.6 volt cutoff voltage at C/6 rate, and different rates actually. And you can see that we've cycled it all the way up to above, actually beyond 50 cycles. So it's a respectable battery. Again, not the best battery, but it works. Now, what Xiaoxing really noticed is that, yeah, okay, it's a battery, all right. But really what's interesting here is that, look at this. There are these little domains that form. And in fact, the formation of the domains seems to correlate with the charge and discharge rate. And so what we noticed is that when you lithiate and delithiate it very slowly, so it's a C/120, very slow rate, right? It tends to form one large domain. These are not simulated. These are actual SEM images that are transformed into pixelated images. So this is all experimental data. All the red and blue things are all experiments. And so what you can see is that as we're increasing the lithiation rate, the domains become smaller and they become more of them, right? So that's what Xiaoxing became interested in. And then he said, well, wait a minute, there's some kind of a coupling between these, within this buckling pattern. And maybe what we can start thinking about in terms of anti-ferromagnetic fields and the Ising model, and maybe some of you are familiar with this, to look at the coupling between any two pairs of nodes, whether they're, what is the amount of coupling and the strength of that coupling. And so what he was able to do is to conduct Monte Carlo simulations. And now, of course, we don't have the lithiation parameter because the Monte Carlo simulations are using thermal tuning knob. And so we have this KT parameter. And sure enough, it seems like the domain formation here scales with a KT. And so what we were starting to learn from this is that you can actually look at these different materials. So silicon, and this is somewhat lithiated silicon, lithium-3 silicon and intermediate, and then some other form of silicon. They form different periodicities within the same structures through these buckling patterns. And actually, since Lattice here, I want to show you something. This is a collaboration with Professor Claudio Di Leo, who is a former student, MIT student, and as soon as this thing comes up, there's a mechanics slide that I wanted to show you. I wonder if it'll let me show it. Is it doing? I'm going to unhide it. There we go.
Next one over.
Oh, this one, yeah. Oh, yes. Thank you. OK. Any day now. It's going to show up, really.
It will.
It will. It just takes time. Yep. Here we go. Right. So we collaborated with Claudio, who then, and we showed him this. We said, well, look, sometimes they buckle cooperatively, where the nodes rotate in two different directions. But when the two nodes co-rotate, it actually leads to a very frustrated type of buckling, right? And so the beams now buckle using with this with a second mode buckling, right? So this is the energetically favorable buckling. This is the energetically unfavorable buckling. And so Claudio helped us come up with this model that explains this behavior. And watch, this is what he discovered, is that as the lithium is going to the silicon, it's not elastic buckling. It's actually plastic buckling. And the color here corresponds to the lithium concentration. And it shows that it yields almost right away, and so it won't snap back. So the novelty in these materials being reconfigurable is that after you lithiate them and you remove the stimulus, it won't snap back. So whatever pattern is formed will be retained until we deliberately delithiate it. And so that's a big difference between the toggling switches that have been demonstrated up to this point, because we can fully control any transient state. So this slide is for you, Lalita. I usually don't show this mechanics part. OK, so the icing model. The band gaps, so these are phononic band gaps. So my student Carlos was able to calculate these dispersion diagrams. And so what we're able to show is that upon different phases of lithiation, you can actually induce different acoustic band gaps. And so that gives us the different reconfigurational degrees of freedom. And so, for example, we can utilize rotation. So this buckling can lead to a pattern rotation. It can lead to out-of-plane buckling over shapes. So you can go from a planar architecture to a hemispherical one. Of course, you can bend, you can expand, and do all these other things. And here's the most important part. The reason why all these domains really form is because of the defects, right? And so you have this coupling between the two. So I showed you that sometimes the beams buckle collaboratively, sometimes they don't. There's something that governs that, right? So it seems like the lithiation rate or the KT parameter governs that. But it's really all about the defects. So there are some defects that are randomly distributed. There's nothing you can do about it, right? There are fabrication defects. Those of you who have made devices, of course, know this. But you can override them, and that's where the icing model comes in. You can actually program your own defects once you understand how they are formed and their effect. And so what Xiaoxing did here is he actually programmed a pattern into this, but you don't know about this. And so all we're going to do now is lithiate it and see if the pattern will show itself. So let's see what happens as you lithiate it, and hopefully you see the pattern forming. And hopefully you see the resemblance. This is what inspired me when you showed me this, the MIT logo that's created out of MIT alum names. This is not quite the same level of complexity, but hopefully you can see the resemblance here. All right, so this is a good point to finish. So just to summarize, as you walk out of here thinking, oh my God, she showed us all these pictures, and it was a lot of information, and I'm not really sure what this was all about. I'd like you to walk away here with one key message. And that is, if you're clever about three things. One of them is the atomic level microstructure of your material. Is it amorphous? Is it nanograined? Is it single crystalline? What is it? The second one, of course, is how your particular material responds to the size effect. And that is, if it's a metal, it might become stronger, it might become weaker. If it's a glass, it might become not brittle. And the third one, of course, is what kind of architecture is optimal for your application? Do you want it to be particularly lightweight and also particularly stiff? That's one thing. Do you want it to be compliant? That's another thing. So there are many design parameters that go into it. But if you are, in fact, clever about those three things, you can create entirely new classes of materials that are exceptionally lightweight and have unprecedented properties but not only properties, but combinations of properties that have never been possible before. And the reason why you would want to do that is so that our kids grow up in a world where there are no more hearing aids, because we'll be able to just write the little cochlea bone. We can. I didn't tell you anything about this, but we've actually been writing tissues, for example, bone tissue, on these kinds of scaffolds at the right scale with the right architecture. So that your iPhone 83, of course, will hold its charge for about a year without needing to be recharged ever. The balloons will not need to be filled with helium because vacuum is lighter than air, so you can evacuate all the air out of it, right? So as soon as we figure out how to make them not be porous, we'll be right on that. Right. The Christmas ornaments, this is very much for the season, right? The Christmas ornaments will never shatter again, but here's the most important pursuit. So maybe you have some of these for your seminars. Maybe you don't, but eventually people generally tend to like brownies, right? So, all right, so what we're working on now are chocolate nanolattices, which are 100% taste, 99.9% air, and 0.01% calories. So with that, I think I'd like to finish, and here's a huge thanks to my group. And all the wonderful funding sources that have enabled us to do this. So I'm happy to take any questions.
Awesome. Thank you for an amazing talk. We have time for a few questions, and there's going to be a reception right after.
Oh, are there going to be brownies?
And a lot more.
See?
So any questions before we break to the reception?
Thank you for the talk. I have a question regarding to the size effect by a slightly different point of view. Regarding the size effect by a different point of view. So when you grow the macroscopic size of your structure, you increase the likelihood that one of the trusses may have an early failure. So do you see that trend that, like, as you make it bigger, that will fail or have a degrading in the performance?
That's a terrific question. So like I said, it's all about the defects, right? So what if you take out, so the question is this: what if you take out one beam? Is that a defect? What if you take out 2 beams? What if 3 beams are missing? Is that a defect? So I think we have to really rethink what defines a defect in a discrete continuum material. And so you chose not to hear about the mechanics, but I would have told you about that. So it turns out that these materials actually have a unique response to flaws. And so that's what the fracture is. So we've done quite a bit actually in terms of fracture experiments. So the probability of having another defect, of course, increases just because by the virtue of making a bigger material, but not by unit, but not per layer. So it's the same density of defects if you think of it this way, because the process doesn't really change. So what does need to be changed is that 2-photon lithography is not scalable. So you can't create a sheet as big as this screen or a textile. So we're very much into textiles now, right? Or any kind of a personnel protection, right? You can't make it at scale using the nanoscribe. So you have to rely on a different type of technology, and that technology might be more susceptible to defects. So what we're learning, the good news, is that it seems like at the nanoscale, all materials become more impervious, less sensitive to flaws in terms of the mechanics, in terms of failure. But the probability of failure very much depends on the defect. So you can either override it with programming your own defects into it, or you can create a different process that will be more amenable to that. Yeah, but that's an excellent point. Yeah. Oh, sorry. Yeah, go ahead. You're the chair.
So when you compress your structures, there's at the beginning, when you compress the structures, there's a large hysteresis, and then it gets smaller, but there's still some hysteresis. So where's the work going? I'm trying to figure out what's happening with that energy.
Yeah. So the first cycle, like I said, is always different, right? That's where you build in a little bit of the pre-damage. And then what ends up happening is that at the nodes, you have these little tiny microscopic cracks. And then they open and close, open and close, open and close. So the second through nth cycle are very similar. And just as you, depending on the integrity of your structure, it should pretty much be the same. But just sometimes you have defects and sometimes you have fabrication details. And so it decreases ever so slightly from second to nth. First to second is always a big drop.
Yeah.
Second to nth is about the same.
Thank you.
Yeah. But it's the history. It's the dissipated energy, right? So it's dissipated through heat, through acoustics, I guess. But it depends on the material.
Go ahead.
So I work in the augmented virtual reality space, and one of the biggest challenges is like making transparent optics that can focus at multiple depths. And in terms of meta lenses or metamaterials, like, have you done any experiments with kind of transparent optics?
We have, but right now they're all in the near IR, so not so much in the visible. To get to the visible, you have to reduce the dimensions so much more. So we haven't been able to do that. Although pyrolizing and general heat treatment is certainly providing a pathway to shrink the dimensions, so that's probably the right approach. And in fact, we collaborated with one of Carl's old students who created structural color. So you can change the color, but we're just not quite in the transparent and the visible range yet. Yeah, but that would be amazing. Yeah.
Let's take one more question.
Oh, Kelly.
I guess it's sort of a related question in a sense. Thinking about the skin depth in metal materials, you said you've done near IR experiments. Is there a refractive index, a composite, I guess, refractive index value for some of these structures, the metal ones in particular?
Yeah, well, so we don't usually work with metals because they're quite lossy. So we go for the high index. So we've worked with germanium, which is a nightmare, and then titania is our next best. So I think it's 2 point something is that. So we work with high index materials, and then NIR is basically is as good as we can get to now. But eventually, I think the combination of the high index material and a much tighter periodicity will give rise to the visible, to the photonic effects in the visible range. Yeah, we're working on it.
Awesome, great. Let's thank Julia again. There's going to be a reception.
Thank you very much.